And I just have a few more like concepts, and then we're going to do some problems. So before we get into some more problems, let's do some concepts. So I kind of mentioned that we'd have different types of symmetry, and we do. They're called even and odd. So we're going to talk about those specifically right now. Okay, you don't want to work today? That's fine. So these are types of symmetry. It's going to get maybe a little confusing in a minute because we're going to do end behavior, which is also even and odd. But when you look at symmetry, we can recognize if something looks symmetric about an axis. And even I think is the easiest one to see that. So an even symmetry is when it's symmetric about the y-axis. Think about if it's an even symmetry, we could literally fold the like graph in half and it would match up evenly on both sides. So what we just did as a parabola, that would be an even symmetry because if you could take it off your page and fold it in half, it would match up completely on both sides. When you were in like elementary school art, did you guys ever paint one half of a picture and then fold it on top and then see that it reflected? Or when you like cut out hearts, do you ever like fold it in half and then kind of cut this way? If you have no arts and crafts experience, I don't really know how else to explain symmetry to you. Just kidding, I could figure it out. But I feel like we do a lot of arts and crafts to make something look nice because if it matches on both sides, that's just symmetry. So think about it that way. If you can fold it in half, it works. Now that's by looking at a graph. Let's talk about if we were solving it algebraically. If I was doing it algebraically, we would say that for all x's, for any number you could plug in, f of negative x would equal f of x. So if an equation, if a function is even, you could plug in negative x and it should give you the same answer as if we plugged in x. I just told you that the last one was even, so let's do an example like that. I'm gonna do an example above it. I know it's not necessarily laid out nicely, but just deal with me. We're gonna do y equals 3 minus x squared. Let's plug an x in to solve. What x could I plug in? Any number. 2. We're gonna plug in 2 and see what happens, and we're gonna plug in negative 2 and see what happens, okay? If I plug in 2, 3 minus 2 squared, well, we have to do our squared first, right? 2 squared is 4. 3 minus 4, that's negative 1. We okay with that? Now I'm going to do 3 minus negative 2 squared. What's negative 2 squared? 4. 3 minus 4, what's that? We plugged in positive x and we plugged in negative x and we got the same answer. So that proves that this is even. Bless you. Again, by looking at it, it's symmetric about the y-axis. By looking at it algebraically and solving mathematically, you can plug in a positive and a negative number and see if they equal each other. Now, if it's an odd symmetry, that one's a little bit funnier to see on the graph, I'm going to be honest with you. It means that it's symmetric about not the x-axis, but the origin. Real quickly, you don't have to draw this, just listen to me. If it was symmetric about the x-axis, it would be like this sideways parabola. Is that a real function? No, right? And we'll talk about this more in a little bit later tomorrow, I think, but it doesn't pass the vertical line test. We talked about the vertical line test online yesterday, right? Okay, so in order for it to be a function, it can't look like that. So we don't have anything that's where it's symmetric about the x-axis, because that's not a real function. If it's odd, it looks something like this. Like a cubic function is odd. Let's see, it looks like this. Like this is like, could be reflected over to be here. So again, I think it's kind of hard to see. So I don't like to just rely on what I see because I could probably convince myself more things are odd than really are. but we're going to look at what it would be algebraically, and I think that's easier to solve. So if I do it over here algebraically, this time I'm going to say the exact same thing. I'm going to say for all x's, if I do f of negative x, it's not going to equal f of x. It's going to equal negative f of x. So if a function were to be odd and I plugged in the negative value, it would give me the same answer as if I plugged in the positive one, but it would give me a negative out front. Let's look at what an example of that would look like. You don't want to work either? Okay. Let's say we had like y equals 3 times x to the third. We're going to plug in a positive number and then that same number negative. What should we plug in? 1, sure. X equals 1. Good. Keep it easy. It's being raised to the third. We don't want to get too crazy here. So we're going to do x equals negative 1 and x equals positive 1. 3 times 1 to the third. Remember to do 1 to the third first. What's 1 to the third? 1. 1 times 3 is? Good. Now I'm going to do 3 times negative 1 to the third. What's negative 1 to the third? Negative 1. What's negative 1 times 3? They are the same answer. They're both 3, but this one's negative. That is reflective of what we have up there. So that shows me it's odd using algebra. Okay? You all right with that? Okay. We're going to actually skip domain for this very second, and we're going to go down here into this empty space, and we're going to write end behavior. So I already previewed end behavior, so I want to talk about that today. Are those words that you heard in Algebra 2? End behavior? Maybe you couldn't tell me what it was, but like, have we heard them? Okay. End behavior is what happens at the ends of your graph, okay? And we have 2 types. We have even and we have odd. I understand we just went over even and odd symmetry, and that can be confusing, but this looks different and feels different, so hopefully we'll be able to keep them a little bit apart. And we don't just have even and odd, we'll have like positive even and negative even, and positive odd and negative odd. So I'll show you what that looks like in a second. Even means that they start and end in the same direction. In the same direction. That means that it either both starts high and ends high like this, or it starts low and it ends low like this. I'm going to show you an example of that. So I'm going to have 2 graphs over here. The first one I'm going to show you is positive. It's if it started high and it ends high. Both of them are going up. That's the same direction. That's a positive even graph because they're going in the same direction and it's going up. The other one is an even negative because they're going down. They're both going down. Started going down, it ends going down. The reason I don't have it like filled in the middle is like I don't know what's happening in the middle. So like end behavior, I don't care what happens in the middle. I just know where the arrows go at the end. Similar idea for my odd. In this case though, I start. What is happening? I start and end in opposite directions. So I remember opposite and odd. I also have positive and negative odd. However, when it's odd, if it's positive, it started low and it's ending high, like this to you guys. It started low and it ends high this way. If it's negative, then it started high and it ends low. Low, low, low. Essentially, the positive and negative refer to like how does it end. So if it's ending high, it's positive. When it was ending low, that made it negative. Ending low, ending low. We have some memories of this. Yes, no, maybe. Let's do an example. Here's a graph. I don't care what happens in the middle. All I care about is my arrows. Positive, because it ends high, and then is it even or odd? Odd, why? Opposite directions, very good. That's it. So I'm gonna draw you a picture. I'm gonna say, is it even or is it odd? And then you tell me, okay? Let's go back really quick to that. Did someone say something? Sorry, sometimes I just bulldoze through. Did you say something, Jared? Okay. Go back to your BFFs for a second because I skipped end behavior. Let's do that end behavior right now. We'll come back to that other page in a second, but let's skip here while I'm thinking about it. Is this one even or odd? Even. Is it positive or negative? Positive. Good. Positive, even. And you can think about it in whatever order you want to write it in. I just make sure I have both of those pieces. Is it positive or negative? Is it even or odd? Awesome. Any questions on that part? All right, let's flip back. Sorry, now I'm doing a lot of flipping on you guys. Now we're going to find the domain. We're going to do domain work right now. If I ask you to find the domain, we want to know what x's can I plug in. And you can think about it one of two ways. You can think about what can I plug in? And conversely, you could also think about like what won't work. What is a restriction that I have? What has to be excluded? What would make it be a problem? We're going to have multiple interval notations based on what restrictions we have. And sometimes we only have one restriction, and sometimes we have several things that we need to fill in. So let's look at the first one. F of x equals x squared plus 4. Is there a number that you can't square? No. You could square any number, a fraction, a negative, a 0. You can square anything. So this one has 0 restrictions. I don't have to exclude everything. I can include every number. So I'm going to do all real numbers, negative infinity to positive infinity. That's the only easy one, so buckle up. Okay, now I'm looking at fraction ones. What's my rule with fractions? What's a problem with fractions? I can have x on the bottom, but what can I not have on the bottom? You could have negatives on the bottom. What'd you say? You can't have I. Very good, but I'm not worrying about I here. What number can I not have on the bottom? 0. 0. If you had 5 over 0, what's 5 divided by 0? No? Undefined. Did you guys ever learn this little cute trick? If 0's on top, it's okay. And if 0's on bottom, it's no. I think someone had to teach me that like a couple years ago, but I think that's a helpful trick. If 0's on the bottom, we have a problem. It's not okay. It is not gonna happen. So essentially what I want is I want to see where would we have 0 on the bottom because I cannot include that x. To do that, I'm setting that denominator x minus 3 equal to 0. Or you can set it to not equal 0, whatever works in your head. Whatever this answer is does not get to be in my domain. It does not get to be included. So I add 3 to both sides. If x was 3, then my denominator is 0. I put the cross through it just so I knew like x cannot be 3. X can be literally any number except for 3. That is my one problem I have. If x can be any number than 3, we've got some intervals we're going to write. Questions before I write some intervals? I cannot let my denominator be 0. So if I had plugged 3 in, 3 minus 3 is 0, and that's no good. Can't have that. That's why 3 is the problem. Okay. Say again. We cannot have 0 be on the bottom. Yes. That's just a rule that we're just going to use for a long time. So sometimes I just have to memorize things like that, even if it maybe doesn't make sense. I'm like, this is just what I have to know. Okay, I started using a number line last class to help them understand what intervals we get to do. You don't have to do a number line. I'm just trying to help us understand. The one thing I can't have on here is 3. So I'm going to identify 3, and I'm going to put an open circle there. I can literally have any other number. So I can go this way, and I can go this way. These are good intervals. So what would that first interval be written as? To what? Go all the way up to 3. Remember, I want you to use parentheses to show that we can't physically be at 3, but we could be at 2.998. That's okay. And then what's the other interval going to be? Good, 3 to positive infinity. I just can't include 3. That's why I have parentheses around 3. It is the only number not there. We okay with that? Okay, let's do the next one. I've got 2 fractions here, so we've got probably 2 restrictions at least. The first fraction is 1 over x. What can I not have in that equation, in that expression? X cannot equal 0. Good. There's nothing to be added or subtracted. We just would plug it in, and if we physically plugged in 0, we would have a problem. What about in the second fraction? X cannot equal what? 3. Is that a movie or is that happening in real life? There's just always such strange video sounds in this hallway. I'm sure they're learning something, but I just sometimes am wondering what. Okay, so it can't be 0 and it can't be 3. There's no other restrictions that we have. So if I were to think about this as a number line again, I know that I can't be at 0, and I know that I can't be at 3, but I could be literally anywhere else. I could be less than 0, I could be between them, and I could be greater than 3. That means that I have these 3 intervals that I'm going to write. Again, the number line is just another way of me teaching this. If you don't like it, don't feel like you have to use it. Some people like to know how many intervals they're writing or how to tell what works and what doesn't work, and that's kind of what I'm using to help us. So sometimes I show multiple ways of doing something so you can find what works for you. Okay, my first interval is negative infinity to 0. I'm doing parentheses. The next interval is 0 to 3. I'm using parentheses. And the last one is 3 to infinity, and I'm using parentheses. How are we doing? Good, bad, middle? See all the thumbs up? Hang it in there? All right, let's do the next one. Ooh, got a lot going on here. Let's look at my denominator first. I've got 2 fractions, or 2 like factors, parentheses. I'm not going to multiply them together. I'm just going to look at them separately. If I had this x plus 1, what would not work? Negative 1. Okay. What about the other one? X squared plus 1. If we were to plug that equal to 0, right? If I was to set that equal to 0, I would get to a place where it would be x squared equals negative 1. Well, what's the square root of negative 1? I. And is I a real number? No, it's by definition an imaginary number. I don't care about i's There's nowhere on my graph to say this is where I is. Are there any real numbers that we can't plug in here? No, because I can plug 0 in, 0 squared is fine, 1 squared is fine. If you plug in negative numbers, you're going to get a positive number. So any real number you plug into this expression right here is going to be okay. So we don't actually have to have any restrictions with that guy. My only restriction with my denominator is that it can't be -1 because of the first parentheses. Are we okay with that? Okay, on the numerator, I have this big radical. If we're only dealing with real numbers, what cannot be under my radical? Negative. Can I have 0 under my radical? Yeah, that's fine. You can do square root of 0. It's just 0. 0 is the smallest thing I can have. So I need to see what can I plug in here that will allow me to have 0 or a positive number. I like to start with 0. What number could I plug in for x to get 0? 4. 4 minus 4 is 4. Okay. Now we're going to go on either side of 4 and see if it's going to be 4 to infinity or is it going to be -infinity to 4. If I plugged in 5, 4 minus 5 is -1. Is that cool under the radical? Nope, not cool at all. What if I plugged in like 3? 4 minus 3, that's +1. Would that be cool? Yeah. So we actually want anything smaller than 4. I want 4 or smaller. So I'm going to write -infinity to 4. No, this is just my pre-work. I haven't even started solving yet. This is all my pre-work to find what my restrictions are. On top, anything between -infinity and 4 works. And on bottom, x just can't equal -1. Now I'm going to go to my number line and kind of see where they intersect. So I've got my number line. I know 4 is important and I know -1 is important. -1, I just can't have, and I can have anything else besides -1. On top, I have to go from -infinity to 4. So I can include 4 and I can go anything less than that. I use 2 different colors because anywhere where they overlap is okay. That's the interval I want. So do you see how I have blue and purple over here? That is an okay interval. I'm going to include that. I can't include -1 because it doesn't have both of them. I am going to include between -1 and 4 because that has both blue and purple. I can't do bigger than 4 though because there's no blue bigger than 4. If you look at my highlight, I only have 1, 2 sections here. Can someone help me write my first interval? Good. And I'm going to do parentheses. I can't include -1. What's my second interval? Good. I want the 4 to have a bracket. So we had to combine kind of a lot of things right there. Let's do one more like that, okay? The next one says radical x plus 3 on top and x minus 2 on bottom. Let's first look on bottom. I think that's easier. What can I not have in the denominator? I cannot equal 2, so I'm not allowed to have 2. What about on top in my square root? -3 is like where it would be 0, and then do I want everything bigger than -3 or smaller? Bigger. Why? Yeah, so if I plugged in like bigger than -3 could be like 0. If I plug 0 in, 0 plus 3, that's okay. I could have a +3 under my radical. So I'm going to go from -3 to infinity. Because I can't equal 0 under the radical. You can equal 3 or 0. Okay, so those are my 2 restrictions. Let's graph them. I have -3 and I have 2. I know that I can't equal 2, so I'm going to open circle, but I'm going to shade everywhere else. And then I have -3 to infinity, so I'm going to close circle on -3, and then shade towards infinity. I'm just going to finish explaining this one, and then we'll clean up, okay? Just like the last one, I see where does the blue and the purple overlap? Good. Good, between -3 and 2, and then where again? After 2. There's nothing to the left of -3, so I don't get to use that interval. I get to start at -3 and go to 2. I get to include -3. I don't get to include 2. And then I get to pick up again at 2 and go to positive infinity. Yes. Yes.